I thought it'd be fun if we all went around and said our name and a little something about ourselves. I'll start. My name is Rod, and I like to party.
This is Nathan Stack. For AP Physics C this year, our end of the year project is to create an instructional video about a certain aspect of physics. In this video, Jason Stack, Chris Van Kerkhove, and I will talk about the physics of stunts using clips from the movie Hot Rod, explaining the mechanics behind Rod's stunt. Our purpose is to see if Jason can clear a similar jump more successfully than Rod, after considering the work Jason will need to do to successfully clear it. In the movie Hot Rod, protagonist Rod Kimball is a naive slacker who believes that he's a stuntman. Through his stunts, he hopes to prove his manhood to his stepfather and earn his father's love and respect. Throughout the movie, he attempts multiple stunts, hoping to maybe even achieve the prominence of Evel Knievel. He's in love with his neighbor Denise, and at one point in the movie, the part which we will focus on, he attempts to jump the town's swimming pool.
Please, God, don't let me embarrass myself in front of Denise.
Hey physics students, my name is Chris Van Kerkhove, and I'm going to be showing you the calculations made to determine how long in the air and how fast Rod would need to be going to clear this 15-meter jump of the pool that you previously saw. Now, the first thing we need to know is the simple kinematics equation, V final equals V initial plus acceleration times time. So what we can do is we can manipulate this equation, assuming that our acceleration in the y plane is gravity. So we manipulate this equation to say time equals V final minus V initial over G. So that's our equation for time. We'll come back to that. Now, we want to know the initial y velocity and the final y velocity when he leaves the ramp and comes down. We're assuming that the ramps are at 45-degree angles, and of course, we assume that air resistance is negligible. So, our V initial and the y is going to equal V initial, the velocity he leaves the ramp with, times the sine of 45 degrees. Now the V final, the velocity he lands on the ramp with, is going to be the negative V initial times the sine of 45. And this is because the ramps are at the same height. So what he goes up with, he's going to come down. Plug in our V final and V initial, we get time equals radical 2 over 2 plus radical 2 minus a negative radical 2 over 2, which ultimately becomes a plus, over gravity. And so that becomes times, of course, our V initial. So that is going to become our time, which simplified down, we get time equals radical 2 over G times velocity initial. So right there, that's part one, that's our time. So now that we got this nice equation right here, we can go ahead and use variables, plug in, and solve for the initial velocity he would need to clear this jump. So first off, we want to know the distance he'd have to travel. So the distance between the two ramps is 15 meters. So for delta x, we can go ahead and plug in 15 meters. Now for time, we go ahead and plug in the equation that we calculated for time previously. So we'll go ahead and take that and plug it in right there. So 15 equals V initial times our time, which is radical 2 over G times V initial. Now there's still one more constant, and that's gravity. And we generally say for gravity 9.81 meters per second squared. So we'll go ahead and use that value for gravity. Now we want to also rearrange so that we can solve for V initial. So therefore, V initial squared, because there's two of them, equals 15 times 9.18 over radical 2, or V initial equals radical 15 times 9.81 over radical 2, and that equals approximately 10.20 meters per second. So through kinematics in the x and y direction, we can calculate the velocity necessary for Rod to clear this jump. So basically what that means, if we're looking at a visual here, he needs to come down here, he needs to leave the ramp at a 45-degree angle at about 10.1 meters per second in order to have enough time and enough velocity in the x direction to safely land on the other ramp.
You can also think of this scenario in terms of energy in order to determine how much work Rod's moped will have to do in order to reach the velocity 10.2 meters per second at the top of the ramp. We're going to make a lot of assumptions here. Let's say the weight of his moped, I'm just going to call that capital M, is equal to 275 kilograms. Let's also assume that a negligible amount of mechanical energy is lost due to friction, meaning that mechanical energy is conserved in this situation. We can also set the top of the ramp, right there, as the zero potential energy level. Where he begins at the top of the ramp adjacent to the pool is about 2 meters higher than the top of the ramp, so making Y initial equal to 2 meters. Also, his bike starts from rest. When he reaches the top of the ramp, all mechanical energy, therefore, is in the form of kinetic energy, both rotational and translational. Therefore, an equation to model the conservation of mechanical energy in this scenario could be this. Now that we have this equation, we can rearrange these terms to find the work done by the moped. So there are a couple things you might notice. This term is multiplied by 2 because there are 2 wheels and each wheel has an equivalent amount of rotational kinetic energy. Also, the moment of inertia of a bike wheel is approximately mr squared, and the mass of a wheel tends to be 1 kilogram, and the radius of a wheel is about 0.622 meters. Now, when we plug in our known values and solve this, we get that the work done by the moped, therefore, is 9014.04 joules. So that's how much work Rod will need to do in order to have that velocity at the top of the ramp, and that's how much work he'll have to do to successfully clear the pool.